So this is the way most things behave, guys. Yeah. A supercritical fluid. It's a substance that is so hot that it can't be a liquid no matter what temperature, no matter how much pressure you put it under. It's a substance that's so hot that it can't be a liquid no matter how much pressure you put it under. A substance that's so hot that it cannot be a liquid or can't be a liquid no matter how much pressure you put it under. And these are really important, these supercritical fluids. When they first came out with decaffeinated coffee, they used a liquid to rinse out the caffeine that we now know as a carcinogen. It means it causes cancer. So they were washing out the carbon dioxide with a liquid that can cause cancer. Of course, there's not much left behind. Tiny little amounts probably wouldn't cause any problem, but it kind of, it's probably not good to be having that in your coffee. Nowadays, they use supercritical carbon dioxide. And of course, it's safe. So now, you need to, I don't know if you need to know this, but I think it's interesting to note that there is no such thing as completely caffeine-free coffee or tea. All they do is reduce the amount of caffeine in the coffee and tea. Okay? In fact, they don't reduce it by that much. If you look at the percentages, kind of small. I wonder what it's worth the money spending on the decaffeinated coffee, but maybe it is for some people. All right. So that's very important. Now, supercritical water is used to do some cleaning that nothing else really works very well for. So those tanker trucks that carry gasoline up and down the highways, gasoline is a mixture of a lot of different organic chemicals, and some of these organic molecules are really long chains, and if you leave the gasoline sitting in the truck, the smaller molecules evaporate out, and the solid ones, those long chains, get stuck on the sides, and you can't get it out. It's a goo that sticks on there. All right. So what they do is they use supercritical steam, supercritical water, and what it does is it cleans it off the sides, and it gets hot enough that it makes those long chain molecules that usually stick, make them evaporate right out of there. So that's a way of cleaning out the gasoline truck. So your gasoline works, better for you when it's in your car. All right. So now let's look at something that doesn't quite behave this way. A really important substance on our planet that doesn't quite behave in this form. This is the way that most substances on our planet behave. But this substance doesn't quite behave that way. So we need another first quadrant graph, Cartesian plane graph. And we're changing the temperature on the horizontal axis just like before. Temperature is going to increase as we go from left to right. And pressure is going to change as we go from bottom to top. Okay, this very important substance has a positive slope between the solid gas phase. When the pressure is low enough that you can't have a liquid form for this substance, it looks pretty much like the other graph. The phase change between the liquid and gas looks pretty much the same. It curves upward all the time. Okay, we still have that supercritical region over here. We got a triple point. Critical point. Supercritical. All that's there. What's different about this really important substance on our planet is that instead of having a positive slope for its solid to gas phase boundary. By the way, all these lines and curves between the different phases or states of matter, they're called phase boundaries. Okay? They're called phase boundaries. So on this graph, that's just a boundary line between the pressure and temperature that makes something a liquid. This should be a liquid, I'm sorry. Between something that should be a liquid and something that should be gas, or a liquid and a solid. Okay? The difference for this very important substance is that instead of being a positive slope, it has a negative slope. It leans slightly backwards. Okay? So this is the phase diagram for water. The phase diagram for water. And it's the only common substance on our planet that behaves this way. There's one other substance that's kind of rare that I know of that kind of behaves that way. Yeah. Yeah. Just make sure you take the pass over here. Okay. Okay. Now, this happens because water behaves like almost no other substance on our planet. This negative slope, that is to say the slope is leaning backwards, the line is leaning backwards, you might say, is important to the way that things work on our planet. Okay? Without that behavior for water, life couldn't exist. Without that behavior for water, life itself could not exist. The fish in the north, further north, where the lakes freeze and stuff, the fish would all die in the wintertime. Okay? And the reason for that is this behavior happens because water expands when it freezes. Okay? That's why your ice cubes float. All other substances, when you put a solid form of that substance in the liquid form of that substance, the solid form sinks. Okay? Solid water floats on the liquid form. Ice floats. Okay? So when we go, if you happen to be able to go further north where you can go skating in the wintertime on a lake or something or a pond, that's because the ice floats. It's also why we have so many landslides in the mountains in the wintertime or the springtime. Because the water gets up under the cracks and stuff. When it freezes, it expands and it knocks the rocks loose. Okay, that's why we have potholes a lot of the time. Because the water gets down in the pavement, and if the temperature gets cold enough, the water freezes and it sort of breaks loose the pavement, and it starts flying up when the cars drive across it. Okay? So having the highways, you know how sometimes they'll take and go and put this liquid stuff to kind of seal up all the cracks in the highway? That helps to keep the potholes from forming because it keeps the water from getting down inside the pavement. So that's all really important to highway engineers. Okay? It's really, if you're building bridges, you've got to take into account the expansion of water when it freezes. If you're an engineer, you've got to know about this stuff. Okay? Really important stuff. All right? You understand the difference here between these two kind of graphs? This is the graph for most everything, and this is the graph for water, which doesn't behave like most everything. Got that? All right? And this, when you look at this, this helps to explain why water can't exist as liquid in space. All right? Or why CO2 doesn't exist as a gas in this room. I mean, doesn't exist as a liquid in this room. It exists only as a solid or a gas. Any questions about this? Now, this is all physical state changes. In this unit, we've looked at both physical changes and chemical changes and the heat involved. The temperature here, temperature, remember, is a relative comparison of how fast molecules are moving in a substance. That's what temperature is. Okay? If you have a higher temperature and a lower temperature, the movement of heat from one place to another, that's the energy. Okay? Higher temperature things have a higher enthalpy. Lower temperature things have a lower enthalpy, and it's the exchange of that enthalpy that is the heat energy. Alright? So we can make things work, we can make things happen by moving heat from one place to the other. And that's how the weather on the planet works. You heat up one part of it, the planet Earth is like a big rotisserie. Alright? You heat up one part of it, some part else is cooling down, and the attempt by the fluids, atmosphere on our planet, to, or even the liquids, the oceans, to get that evened out is where we have all the wind and all the weather and stuff. Yep.